We will recap another concept we already looked at, the gravity waves. Why are we doing this? Basically, we will look for similar processes in the ocean, obviously, with the density differences and topography and boundaries and so on. So we had looked at the parcel ideal gas relation. Rho of the parcel is P of the partial divided by RT of the parcel, and we can replace hydrostatic balance means the pressure of the parcel instantaneously adjusts to the environmental pressure. So PP can be replaced by PE at ZP divided by RTP. So you're displacing a parcel by delta and moving it into a new environmental pressure, and we are going to look at how gravity waves can be generated. Why are they called gravity waves? Again, because you are in a buoyant air column. When you displace air parcel, depending on its buoyancy, it'll continue to go up if it's unstable, or it'll be pulled back down if its buoyancy is greater than the new location, new environment, in which case what is pulling it down? It's the gravity. That's why we call it gravity wave, right? It's pulled down, overshoots its neutral position, goes back up, and depending on the dissipation, etc., you get gravity wave. So gravity pulling it down with minus g rho p delta A delta Z, which is its mass. The volume times density is its mass. And net pressure force from the top and the bottom, we had minus delta PE delta A. All are small, so we can take local gradients in that sense. That's equal to G rho E delta A delta Z. Okay, what did we do? We again are basically using ideal gas laws and so on. So writing our balance, Fg plus Ft plus Fb, gravitational pull, pressure from the top, pressure from the bottom, can be written as G rho E minus rho P delta A delta Z, right? You know that the gravitational pull is going to depend on the relative density change because we are in a continuously stratified fluid, and that's where our reduced gravity will come in as well. Okay, so rho P delta Z delta A, d squared delta dt squared, the acceleration term should be equal to the net force, which is G rho E minus rho P delta A delta Z. This is very simple derivation. You can make sure you understood it going back to the podcast from the 4th chapter. Why are we doing this? Basically to derive the wave equation. As soon as you see a square term equating to a negative term, you know that wave solutions are going to come out of it because of imaginary terms in the solution. So using our ideal gas law and our potential temperature relation, we wrote buoyancy, or the reduced gravity as we refer to it at some point, written in terms of temperature or potential temperature. Okay, we are easily exchanging between them to account for pressure effect, right? The theta allows us to include the pressure effect into in situ temperature. So for small displacement delta, theta E at Z plus delta is going to be theta E at Z plus delta is going to be theta E at Z1 at the original position plus delta times d theta E dz, the gradient, right? Delta here is the delta Z. We sometimes call it delta Z. In this case, we are calling it delta. So theta of the parcel minus theta of the environment in that case is minus delta times d theta E dz. You have moved up the parcel, right? So the temperature has to decrease, but remember theta E theta goes up, right? So you are moving it from a lower altitude to a higher altitude, so you're moving it from a lower theta to a higher theta. So d squared d delta dt squared is minus g rho p minus rho e or rho p. So you place it with the theta E relation we produced, and we are back to our familiar buoyancy frequency, so that ends up as minus n squared delta. Obviously n squared is positive, so this is a negative term, which means we are going to get wave solutions. So n squared is g over theta E d theta E dz. So sigma is using the switching now to the ocean. I jumped there. We will try to do the same thing. Sigma is sigma 0 plus rho ref times minus alpha t delta t plus beta s delta s. Okay, so how does it work in the ocean? The ocean is positively buoyant if d rho dz is greater than 0. d rho dz is greater than 0 for the environment. It's neutrally stable if d rho dz is 0, and negatively buoyant if d rho dz is less than 0. So unstable, stable, and unstable, neutrally stable, stable, right? So that's all we have to do, and we have to then translate it into gravity waves. Going back to this relation, we write it in terms of rho, because in the ocean it's convenient to go back to density. In the atmosphere we kept getting rid of density and going into pressure and temperature, because density is a very inconvenient variable to carry. But in the ocean, if it's incompressible, then density is not a big problem anymore, because remember, even the continuity equation could be approximated as non-divergence equation, right? So density is not as much of a problem in the ocean, so we often carry density, but we will end up making other approximations where relating to rho ref and sigma, the deviation from rho ref. So we can carry sigma around and look at gradients of sigma in the horizontal and vertical. Okay, slightly different manipulations, but the concepts to remember again are the large scale thermal wind balance, and hydrostatic balance is still there, and we're going to have geostrophy, of course, which means we are going to end up with geostrophic shear as well. Okay.